Good morning, ladies and gentlemen. All right, this is a little video on how to think about going about making your instrument. I'm not going to tell you everything. I'm going to make you do a little research. But let's get started. So far, you have a formula for the speed of a wave, which is your wavelength times the frequency. And that's going to come in handy for us today. There's another formula for speed of a wave in a string, which is applicable for us because we're making string instruments. It would be a lab we would have done in school, but obviously we're not doing that. So you can also figure out the speed of a wave in a string by doing V equals the square root of the tension in the string, which is why you have those knobs at the top that you can tighten it up or reduce the tension, divided by the mass per unit length. Now, let's do a quick little check on this, because that does not look like it would come out to be the units for speed or velocity, which is meters per second. Let's check it out. If we do a unit analysis, tension's in the top. Tension's a force, and a force is mass times acceleration. So your mass is in kilograms, your acceleration is in meters per second squared. That length is in meters. So if you do the flip thing, that would put meters up top. That would give you meters squared per second squared. Now that's all divided by mass, which is in kilograms. That cancels, that cancels. Take the square root of meters squared over second squared, and you get meters per second. So check, bam, it works. So you're gonna make an instrument. Let's see, I do my best drawing here of an instrument. There's some kind of ukulele, a guitar, or violin, or cello, whatever it is. Got a hole in here, makes it resonate nice in there and sound nice. I'll let you experiment with that. Then you got the top of the instrument here with the pegs that increase or decrease the tension. I'm going to change this formula slightly because we're going to be putting on set strings. We're basically not changing the mass per unit length on each string. All right, as you put on different strings, yes, that changes, but on a set string, it really doesn't. So I'm going to change this around to V equals the square root of T over mu. I'm going to call mu is the basically the density, mass per unit length of the rope. You can think of it as density. So let's say we want to figure out where we place our first fret. This one down here is going to be set. However, as you look up the instrument, we have bars over here. I'm pretty sure they're called frets. And when you press it, it seems to change the sound. So let's go into that. Let's calculate the length the string needs to be for an E note. Let's say we want to put an E right there. Well, we want essentially this string to vibrate at exactly a certain frequency that's going to make the air resonate and vibrate at the frequency of an E note that our ear perceives as an E note. It's kind of the reverse of what you saw with the Tacoma Narrows Bridge. There, moving air hit the resonant frequency of the bridge and made it oscillate. Here we're going to wiggle the string to hit the frequency of the air that we want our ear to hear. So I want to look this up. E note has a frequency of, where did I put it? 8.241. 82.41, sorry. And that's in hertz. So we're going to use this formula and use the speed of sound on an average day, which happens to be 343 meters per second. So that's our V equals lambda F. I want to figure out what the wavelength has to be to oscillate at a frequency of 82.41 hertz. This changes day to day, which is why you need to be able to play with the tension so that you can get the velocity right so that this formula works on your instrument. Also, on a given day, temperature goes up, down, humidity in the air, it's all going to affect the speed at which sound moves that day. So you have to be able to tune it. I divide over into there, you'll get lambda equals, where's my calculator? 4.16 meters. That's pretty long. That's like 15 feet. I'm going to let you figure that one out. And your hint here is do a little research in octaves. I don't want that full length because I'm going back up to my picture here. When this vibrates, let's say this is this side of it and this is a blown up picture of that fret. When you pluck a guitar string, you have a node here where the wave form can't move, and you have a node here where again the string can't move. It's going to, it's going to vibrate up and down in a standing wave like this. Now that's not a full wave, that's half a wave. The full wave would be all the way out over here, right? All the way down, all the way up, and back to where you started. So I got half this number. So that would be 2 and 16, 8. That would be 2.08 meters. That's a 0. Still, over 6 feet. That's a big instrument. Go look up octaves, figure this one out. That would tell me I would place this fret, glue it on, nail it on, whatever you got to do onto your instrument, exactly 2.08 meters away from the bottom fret that can't move. That's this one. Let's go to a next note. Let's go with D. D has a frequency, and you do just what I do. I looked it up, 110 hertz. I'm doing the same thing over and over again. Now I got to go into V equals lambda F 343 equals lambda times 110 hertz. That's the frequency at which we want this string to vibrate this time, which is going to make the air vibrate at that frequency, which hits your ear and you perceive as a D note. Divide this over. I get 3.12 meters. So lambda full wavelength equals 3.12 meters. Half of that's 1.5, half of that's 0.06, so that would be 1.56. That would be my D note. Here's my E. Whoops. For my D note, I have to place a fret there, so when I press my finger on it, I have now shortened the wavelength, right? Shortened the wavelength from there to there, increasing the frequency from here to here, and producing the D note, which is of a higher frequency, higher pitch. It's kind of like, let's see, it's kind of like if I took a ruler. How do I do this? Stay there. Oops. I took the ruler off the edge of a table and I flick it like this. You hear a certain sound. It's got a certain frequency and wavelength, but if I pull the ruler back, you hear that frequency go up. You hear the pitch go up because the wavelength of where it could actually vibrate got shorter. It's kind of what you're doing with your instrument. And around the reason we have different width of strings is because that you can vary this. So you'll notice as on your strings, as you get the fatter and fatter strings, the mass per unit length goes up. You get the same exact length of strings because, and I say the strings, I mean wherever you press your finger down on the fret, that's going to now manipulate the length of the string or the length of the half wave that's vibrating. As the strings get fatter, their mass per unit length goes up. As the denominator of a fraction goes up, the value of the fraction goes down. So you're reducing this. So if you reduce that and you can't change the length of where that, or you nailed or glued that fret in, that has to reduce then the frequency because that can't change on that string. That's why you get that deeper sound when the heavier strings are plucked. There's your basics. Go look up octaves because there's no way we're making 6 foot long instruments. There's something going on there. That's for you to figure out. Good luck.